Why my camera? No available camera found. What happened? I have problem with my camera. Assalamualaikum. Good afternoon, everyone.
Good afternoon,
Prof.
Okay, I have problem with my camera. I cannot on my camera. Why?
It's okay, Prof.
Okay, so I start sharing my my slide. Okay. Okay. Last week, actually we have this. We have talk on. Okay. Screen. Okay, can you all see my slide?
Yes, Prof.
Okay, so actually last week we have talked about water hardness and also the precipitation system for removal of the hardness. So everyone knows that this parameter, the calcium and especially calcium and magnesium precipitate or hardness found in groundwater. So the removal system, the removal of this pollutant is we have several few types of removal system, and we have looked at precipitation. Precipitation of hardness. Last week, I also have given you quiz on converting unit for hardness. So I hope that you all can do it. Okay, so the first system to remove this water hardness is by chemical precipitation. So so usually when you have this waters, you have water hardness, and you want to remove this hardness using chemical precipitation. So this is the sequence. Usually you use the lime soda ash at the beginning of the treatment sequence, where you have this lime and soda ash. Sometimes you can also use together with your coagulant tank if you want to remove the, you have learned about removal of clay and minute particles of clay using coagulation. So this is where you put the treatment unit. Okay, so I just want to continue example. Calculation for removing the carbonate hardness. So this is the procedure how you control. Can you all see? Can you all see the screen?
Yes,
Okay.
Prof.
So, okay, the lime dosage calculation for removal of carbonate hardness. So the lime soda ash water softening process uses lime and soda ash, sodium carbonate, to precipitate hardness from solution. So carbonate hardness, as we have discussed, due to calcium and magnesium bicarbonates, is complex by lime. That's why you can remove the precipitate using lime. Non-carbonate hardness, the calcium and magnesium sulfates or chlorides requires the addition of soda ash for precipitation. So carbonate hardness, you can use lime, but non-carbonate hardness, calcium, magnesium sulfate and chlorides can only be removed using soda ash. So the molecular weights of various chemicals and compounds used in lime soda as a softening calculation are as follows. This one are all the molecular weight for most of the lime and soda ash, the softeners, that commonly used. So it's easy for you. I think if you can remember also the molecular weight for each element in the periodic table, you can also get the molecular weight of the compound, chemical compound. So this is the example, how you calculate quick lime or hydrated lime dosage in milligram per liter for determining the amount of chemicals needed for removal of your water hardness. So let's say if you use quick lime, quick lime is CaO2. Calcium dioxide. This is quick lime. Let's say if you want to use quick lime, where you can only remove the calcium and magnesium bicarbonates, you use the formula here. So quick lime in milligram per liter, A plus B plus C plus D times 1.5 divide by lime purity. So why A is due to CO2 in source water, meaning that although CO2 is not pollutant, water hardness pollutant, but you need to calculate the amount of lime that you need to remove this CO2, because CO2 will also react with lime. So that's why you have to calculate the amount of lime used by CO2 in your source water. Okay, so CO2 in source water, milligram per liter as CO2 multiplied by 56 is the lime. Quick lime molecular weight, divide by 44 is the molecular weight of carbon dioxide. So A, and then you need to add the quick lime used for bicarbonate alkalinity. So milligram per liter as calcium carbonate multiplied by the quick lime divide by the bicarbonate alkalinity. Alkalinity as calcium carbonate, the molecular weight is 100. Okay. So, and then C, hydroxide alkalinity in softener effluent. If you use hydroxide alkalinity, so the molecular weight is also 100. 100 here. Okay, and then you need also to remove magnesium. Magnesium, because usually you cannot have magnesium in certain concentration. So if you have magnesium, you also need to remove from your water supply. So you use 56 because you will be using time divided by the molecular weight of the magnesium, which is 24.3. And you multiply here by 1.15 is you want to provide excess lime dosage, because you want to make sure that all the water hardness is removed. Okay, for hydrated lime dosage, use the same equation as above, except you substitute, instead of you use 56, you substitute by 74 when calculating A, B, C, and D. So this is hydrated lime. So you can use both, depending on what, depending on your preference. Okay. And so this is the example. A water sample has a carbon dioxide content of 4 milligram per liter as carbon dioxide, total alkalinity of 130 milligram per liter as calcium carbonate, and magnesium content of 26 milligram per liter as magnesium. So usually you need, when you design your water treatment plant, you need to spell out the amount of whether any water softeners that you use, the amount that you need for your amount of water. So approximately how much quicklime, let's say, because usually when you buy these chemicals off shelf, it is not 100% purity. Let's say the quicklime is 90% purity, will be required for softening. Assume 15% excess lime. So this is the formula here. Okay, and now determine how much hydrated lime will be required for softening a water with the same characteristic. First, it is easy that you just use the formula here. Okay, you follow the formula for the calculation, and then what you get here, you calculate the quicklime dosage. So with 90% purity, you divide by 0.9. So this is the concentration of the quicklime in the feed that you need, 176 milligram per liter quicklime. Okay, so this is just the concentration, not the amount. But when you design your water treatment plant and you want to use this precipitation system of removing your water hardness, then you need to determine how much amount of calcium quicklime or hydrated lime that you hydrated calcium that you want to use for your water softeners. Okay, so let's say you use hydrated lime dosage. Then you just substitute the lime with hydrated lime. Hydrated lime meaning that you buy the chemicals with water in the with H2O molecule in the compound. So meaning that it is not the concentration of lime is less. So you can see here the molecular weight is 74. And finally, you will get the concentration of lime dosage. So you can see it takes more hydrated lime than quicklime to soften the same water, because you are using compound with OH. Okay, now you can determine the feed rate for the hydrated lime or quicklime by multiplying with your incoming flow. So this is this is the dosage that you have just calculate, and you multiply by the flow. Whatever you need, you make sure that you get conversion right of your unit. Okay, this is how this is one of the important things for the water hardness part that you need to know, the calculation of the chemicals that you need. Okay. So this is the feed rate just now. It's just multiplying by the chemical dose, which is the concentration by flow rate. So you'll get the amount of in kilogram per day the amount of chemicals that you need. Okay, so this is the end of the slide for water softness. Okay, so hardness can be removed by chemical precipitation. This is one of the technique to remove water hardness. Okay, you can also I'll go into my second slide. Still on removing water hardness. Okay. Okay, ion exchange. So, okay. You can also, it's up to you which method you want to remove. If you have water hardness, 1000 milligram per liter of bicarbonate, then you need to make sure that in your water treatment plant you have this unit operation to remove the water hardness. Okay. So definition of ion exchange. Ion exchange is a unit process in which ion of a given species are displaced. Hold on, give me 5 minutes. Okay. Okay. Ion exchange is a unit process in which ions of a given species are displaced from an insoluble material called resin by ions of a different species in solution. So the exchange ion have the same charge. That is to say, positive ions are exchanged for positive ions. So you have this magnesium and calcium in your water characteristic. So it will be changed with sodium. Sodium is not element of water hardness. So you exchange magnesium and calcium with sodium. So OH minus is exchanged for nitrate. So meaning that whatever there is a rule. When you want to remove magnesium and calcium and you have this OH, then what you need to use for your resin. So the exchange resin is either a naturally occurring material such as zeolite or synthetic organic materials. So resins can be either cationic or anionic. Okay, the resins are usually beads or granular particles having a size of about 0.1 to 1 millimeter. Okay, so this is zeolites. Zeolites usually is a naturally occurring materials. They are microporous aluminosilicate minerals. So you also use zeolite as adsorbents and catalysts. But usually in your ion exchange process, you use more synthetic organic material. So this is naturally occurring material, and you can also use synthetic organic material. Okay. Okay, types of ion exchange resins. Both anions and cation resins are produced from the same basic organic polymers. They differ in the ionizable group attached to the hydrocarbon network. It is this functional group that determines the chemical behavior of the resin. Resins can be broadly classified as strong or weak acid cation exchanges or strong or weak base and ion exchanges. Okay, so you have this zeolite and you also have synthetic organic polymers. So in your water treatment plant project, if you want to use this ion exchange, these are all must be specified. Let's say if you want to remove hardness, then if you use this ion exchange system, then you need to specify the types of resin, whether you are using zeolite, and then you need to justify why you choose this, or you choose synthetic organic polymers, maybe because of the cost, because of the easily available materials. So these are things that will give you extra mark to your choice of unit operation. Okay, these are photos of ion exchange resin. Resin very small actually. The largest is 1 millimeter diameter. And this is an ion resin, and this one is cation resins. So the ion exchange process, so we want to know how this ion exchange process is happening. So calcium and magnesium ions that cause water hardness can be removed fairly easily by using an ion exchange procedure. Standard water softeners are cation exchange devices. So you can always buy off shelf. Cations refer to positively charged ions dissolved in the water. So cation exchange involve the replacement of the hardness ion with a non-hardness ion. Like when you replace calcium and magnesium ions, they are cation of water hardness. You replace with a sodium, which is non-hardness ion. So water softeners usually use sodium as the exchange ion. Sodium ions are supplied from dissolved sodium chloride salts, also called brine, sodium chloride salts, because Cl will be exchanged with maybe HCO3 or CO3 bicarbonate. In the exchange process, sodium ions are used to coat and exchange medium in the softener. The exchange medium can be natural or synthetic, just now that we have discussed. To recharge the softener with sodium ions, a softener is backflushed with a salt brine solution. So usually you have already coated the resins with all this sodium. So then you need to remove the sodium because you want to still use the resins. So you have to recharge the softener. So how do you recharge the softener? You can recharge the softener with sodium ions. A softener is backflushed with a salt brine solution. Okay, during a backflush, the brine solution replaces the calcium and magnesium ions on the exchange medium with sodium ions from the salt solution. Okay, so you see here, this is the softening process. So you input here the hard water containing calcium and magnesium. These are the resins. So you can see the rectangular here is there are magnesium ions pattern, the rectangular patterns, and these are the red one are calcium ions, and these here are the sodium ions. So ion exchange resin with sodium attached. So you have this hard water containing calcium and magnesium into your column, and you will get softened water containing sodium. Okay, so because you have exchanged, you have exchanged the magnesium with sodium, but still you will have extra sodium in your water, because you have already taken out sodium from the resin. Okay, so after that you have this wastewater containing calcium and magnesium. This one you recharge. You recharge the resin, meaning that you clean the resin. You clean the resin with brine solution containing sodium. So you will get wastewater containing calcium and magnesium. Okay, so you will get your wastewater containing calcium and magnesium out of the system. Okay, so after softening a large quantity of hot water, the exchange medium becomes coated with calcium and magnesium ions. When this occurs, the exchange medium must be recharged or regenerated. Firstly, you get these magnesium ions coated on the resins, and then you have to recharge or regenerate, where you want to remove the magnesium ions attached on these resins into the outflow from the system. So the recharging process, the time between recharging cycles depends on the hardness of water, the amount of water used, the size of the unit, and the capacity of the exchange medium to remove hardness. So these are all the criteria that affect the recharging cycles time. How long do you take? How long do you need to recharge your? Meaning that how long it will take for you to clean your column, your ion exchange column. Okay. Okay. So, health risks associated with softened water. During the softening process, sodium is released from the exchange media into the output water. For every grain of hardness removed from water, 8 milligram per liter of sodium is added, meaning that you have attached the calcium and magnesium on the surface of the resin. Then you have to recharge, meaning that you have to clean the resin from this calcium and magnesium, still using sodium, still using the sodium chloride containing water. So sodium is added. So meaning that the water that will get will contain a lot of sodium. So people on restricted sodium intake diets should account for increased levels of sodium in softened water. So it is a problem sometimes, because after you regenerate, you will get treated water with lots of sodium content. So sometimes you exchange sodium with potassium chloride, because potassium is something that you will need more in your body. So it's not dangerous for you. So sometimes you substitute with potassium chloride, but potassium chloride is expensive. Okay, and of course it will add to your cost. About 10% more potassium chloride is used during the backflush operations. Okay, so sometimes if you have this problem, you have hard water problem in your water supply, what people will do if they have two pipes. First, they will have pipe for potable water, meaning for you to consume, you use just the hard water without cleaning it, because actually calcium and magnesium in small amount of quantity will, as we have discussed last week, it's not dangerous to your health. Okay, but because this hard water, they will prohibit the formation of bubbles in your if you use your soap, and also it will also cause other problems with precipitate in your pipe system. So you will have problem. That's why they will but if you use this ion exchange, usually you will get more sodium chloride or potassium chloride, but it's expensive in your water supply. So usually sometimes if water hardness cannot be avoided, people will have two different pipes in the kitchen. One for you for you to consume, and another one is for you to for other things, for washing, for many things that you don't want this water hardness to affect all the piping system. Okay. So cationic resins are materials that have reactive groups that can give up positive ions in exchange of other positive ions from the liquid phase. So anionic resins are materials that have reactive groups that can give up negative ions in exchange of other negative ions from the liquid phase. So the exchange of ion is governed by the relative preference and the strength of ions to replace others. Yeah? So you will see that here preference ratios which ion exchange. Yeah? For cation exchanges, let's say you want to cation exchanges, you know that you want to remove magnesium. So you know the most the most strong cation exchange for the cation exchange is when you use barium, yeah, and then it's followed with plumbum, strontium, calcium, nickel. So meaning that usually your water hardness is due to magnesium, due to calcium, due to strontium. So meaning that let's say if you want to remove strontium carbonate, strontium dioxide hydroxide, you want to remove. So you need to use whether plumbum or barium, because the strong one will replace the less strong cation. Okay, and for anion exchanges, you can see that sulfate will remove whatever anion that you have in your compound. Okay, so but the strength of all these cation and anion will depend on the reference series that you can refer here. Okay. So ion exchange chemistry, sodium cation exchange or softening, you can see calcium is exchanged with something, you will get the R, okay? Actually, they just exchanging the positive is positive, the negative is the negative. Regeneration using strong brine sodium chloride, and then when you have this resin coated with magnesium, the resin and calcium, you need to remove because you need to use the same resin. Of course, you cannot afford to always replace the resin, so you need to regenerate. So you use strong brine, which is sodium chloride, and you will get this in your water, in your water that you have treated. So if you have health problem, then this is something that you need to consider, because you do, maybe you need to replace with potassium, or you use different other techniques to remove this water hardness. Okay. Okay, this sodium type ion exchange resin, you can see here. You can buy off shelf, ion exchange resin. This is the sodium type. And you can also have deionizing type ion exchange resin here. Okay, you can buy off shelf. Okay. Regeneration of ion exchanges. Just now we talked about regeneration because you want to use the resin again. So you can afford to always replace with the new ones. So each resin has a limited capacity of exchanging ions. After a certain time of operation, the resin reaches its maximum capacity, meaning that all the surface area is covered by whether calcium or magnesium ion. And no further ions are removed from the liquid phase, meaning that if you just ignore this operation time, it's already hit its maximum capacity, meaning that it will not be removed if you just apply to your unit. At this point, it's said to have reached the breakthrough concentration similar to adsorption. So you have to learn about adsorption. So breakthrough concentration is reach. After reaching the breakthrough concentration of the cation or anion under consideration, the ion exchanger tank is taken offline. Okay, so you need to off your operation. For sodium exchangers, a strong brine of sodium chloride is pumped in the resin bed to add the sodium ions to restore the exchange capacity of the resin by replacing the cations that were attached to the resin during operation. The strength of the brine overcomes the strength of the bond between the cations and the resins. Okay, so you generate. So this is the typical ion exchange installation. I think if you go and visit industry, it is very common that you have ion exchange, not only for water hardness, but also for absorption. That's why it is very common because it's easier to install. It is very compact. So you can have this. You can buy this unit treatment of shelf. Okay, configuration of the ion exchangers. So when you want to design in your water treatment plant, you need to know the configuration that is allowable or that is commonly used in your system. The main component of the ion exchangers is a cylindrical steel tank with the following typical dimensions. Diameter could be 1 to 2 meter and height 3 to 4, typical to the absorption tank. That's why when you see, there's not much different from one industry to another when they use this ion exchange. Okay, so the height is 3 to 4 meter. The ion exchange bed occupies 1 to 3 meter of the tank height and supported from the bottom with an under drain system. So in your height 3 to 4 meter, only 1 to 3 meter is occupied by ion exchange bed. So the water enters from the top down flow by an influent distributor piping system and applied at the rate of 0.5 to 7 liter per square meter per second per square meter. Okay, so this is the range when you want to use this ion exchange. So when you do your treatment plant and you use ion exchange, I want to see the specification that you choose for your system. When breakthrough is reached, the tank is taken offline and backwashed by applying water from the bottom outwards to remove any suspended solids. So it's like sand filtration. Sand filtration, they also have a backwash system to remove whatever blockage or solids that in the voidage of the of the media or the resin. Okay, after backwashing, the regeneration solution is also pumped from the bottom upwards at the rate of 0.7 to 1.5 liter per second square meter. Okay, you always have this range, and actually when you do and when you carry out this treatment, and then the backwashing or the cleaning like this, the regeneration, you can start using any numbers within the range suggested by your references. But then after you run the system many times, you will find which rate is the most suitable for you, for your system. Okay. So that's why you can just choose. It's not very definite, but you can just as a guide the rate that are suggested by references in research. But after a certain time, you will notice what is the best rate for your system. Okay. Okay. The same influent distributor is used to drain the outflow backwash water and the regeneration solution. Okay, the brine, acid, or base. At the end of the regeneration, the bed is washed with clean water to remove the residual of the regeneration solution. And under drain piping system is installed at the bottom to collect the treated water and used to pump the upflow backwash water and the regeneration solution. Okay, so you always can collect your water under drain piping system. Okay. So the pre-treatment, okay, so this is important for you to notice. Let's say if you want to use ion exchange, please bear in mind that the influent to the ion exchanger should be filtered to remove turbidity. Okay, so meaning that when you arrange your system, make sure that turbidity is removed before you direct your effluent to the ion exchange system. Dissolved organic matter should be removed by granular activated carbon before the ion exchange because the organic may coat the resin and reduce its exchange capacity. So this is a more expensive treatment. So might as well you use the granular activated carbon filtration or any type of filtration because you just want to make sure that less organic that can coat the resin and reduce the exchange capacity. So the ion exchange is efficient for TDS less than 1000 milligram per liter. Okay. Okay. Then sizing ion exchanger. The sizing of the ion exchanger depends on the following factors: contact time, hydraulic loading rate, resin depth, and number of columns. So these are the parameters, design parameters that you need to specify whenever you use this ion exchange system. Okay. Ion exchange process analysis in the fixed bed. We always call fixed bed because the resin is fixed. They put in the, they make sure that there is under drain system and you put this resin on the in the column. Mass transfer inside the ion exchange bed. When the polluted water is pumped on the ion exchange bed, the pollutant ions replace the exchangeable ions in the resin. Okay, so the area of the ion exchange bed in which the exchange occurs is called the mass transfer zone. So no further absorption occurs below the MTZ, and the water leaving the MTZ zone contains the minimum concentration value of the pollutant that the bed can produce. Okay, so when the mass transfer zone is okay, so this is where the ion exchange occurs. With a time zone of saturation is created above the mass transfer zone in which the resin has reached its maximum exchange capacity and no further replacement occurs. So there is a time zone of saturation, meaning that when you pass this value, finally actually you don't get any softening of your water. So the equilibrium concentration of CE of the pollutant in water in this zone is the same as CO. So you want to make sure that whatever that you have generated or you treated, you will have the CE should be the same as CO. CO should be the same as CE. Okay, the zone below this mass transfer zone, essentially clean zone and no adsorbed material on it. With time, the saturation zone depth increases and the MTZ is pushed down until we reach to a point where the clean zone disappears and breakthrough occurs. Okay, breakthrough is said to have occurred when the effluent concentration reaches to 5% of the influent concentration, meaning that breakthrough, meaning that you must stop your operation whenever you find out that there is 5% of your hardness is in the treated effluent. Okay, so after additional time, the mass transfer zone start to decrease until it disappears and the bed is called exhausted. So exhaustion of the bed is assumed to have occurred when the effluent concentration is equal to 95% of the influent concentration. So actually we must stop during breakthrough. We cannot wait until the system is exhausted. Okay, the length of the MTZ is calculated from the following equation. So you can just use this equation to do the calculation. Okay. The area above the breakthrough curve is equal to the mass of pollutant absorbed in the column and equal to here. This is the X, but I don't. Okay, so the length of the MTZ is calculated from the following equation. Okay, so you want to know what is the length of MTZ, so you can use this equation. Okay, and you can see here, this is the exhaustion when 95% of the hardness in the influent is also at the effluent. So the breakthrough is when you start having, actually you stop during breakthrough. So this is the exhausted, this figure here showing, represent the time when the column is exhausted. This is exhausted, the blue one. This is the mass transfer zone, and this is the clean zone. So we will have this breakthrough when we start this 5% of your hardness in the treated effluent, and actually we must stop our operation by that time. Okay, you can also use multiple tanks operation. Ion exchange tanks can be operated in parallel or in series. A minimum of 2 parallel carbon contactors is recommended for design. Multiple unit permits 1 or more units to remain in operation while the unit is taken out of service for backwashing and generation or maintenance. Okay, so that's why at least usually you have 2 tanks in series, because you can always use one of the tanks if one needed for backwashing, generation, or you need to service the system. Okay. So this is, so in your water treatment plant, if you use ion exchange, so I also want to see whether you provide only 1 tank. So meaning that you don't have any plan for emergency, or you can have a few tanks in series. Okay, that one is also considered sustainability in your design. Sustainability is when you can make sure that there is no factors or issues that will stop the operation totally. Okay, so you need to always think about having another system when you need to backwash or you need to service the ion exchanger. Okay, and okay, exchange capacity of ion exchange resin. Ion exchange resin have a limited number of exchange sites available, as we have discussed previously. And the total solid phase concentration is termed ion exchange capacity. For cat ion exchange resin, Q0 is in the range of 200 to 500 milli equivalent per liter per 100 milligram of resin. During the exchange, the resin should be electrically neutral, thus all the exchange sites should be occupied either by the original ion, such as sodium, or by the replacing ion, such as calcium and magnesium. Okay, and the ion exchange occupancy should be equal to Q naught at any time. Many equations were developed to determine exchange capacity. So the most famous equation is the Thomas kinetic equation. So you need to determine the exchange capacity using this equation. And this is the Thomas kinetic equation for ion exchange capacity. So you will be able to tell after how much volume, then you need to start backwashing the system. Okay, so this is the equation, and actually this is equation is in linear in the form of y equal to mx plus c. So the slope is here, k1 c naught over q, and the intercept is k1 q naught m over q. So you can see what this symbol means. C, effluent concentration of the ions. C naught, influent concentration of the ions. K1, the rate constant, maximum solid phase concentration, mass of resin, throughput volume, and flow rate. Sometimes you need to know the mass of resin. Sometimes you need to know what is the volume that you need. So this equation will help you. Okay. So this is one example how the ion exchange exercise. So an industrial water with 107 milligram per liter of copper, 3.37 milli equivalent per liter, is to be treated by an exchange column. The allowable effluent concentration C out is 5% of C in. A breakthrough curve has been obtained from an experimental laboratory column on the sodium cycle. So these are the data concerning the column. So you can always start your experiment and you can get the breakthrough. Then you will usually know actually the exact amount of resin and that you need to use. So these are the diameter, inside diameter of the system, 1.3 centimeter, this small one. Length 45.7 centimeter, the mass of resin, the bulk density of resin, and the liquid flow rate. This is a very small, just lab scale system. So the design flow rate will be 378,500 liter per day. The allowable breakthrough time is 7 days of flow, and the resin depth is approximately twice the column diameter. Using the kinetic approach to column design, you need to determine the kilogram of resin required, the diameter and depth, and the height of the sorption zone. So this is the solution. So let's say in column 1 and column 2, you have this data from the experiment. When you here, when after you have input 15.9 liter, you will get in your outside from the system is 4.45 milligram per liter. So the data in columns 1 and 2 are used to draw the breakthrough curve. And the data is arranged in columns 4 to 5 and 6 in the form necessary to plot the Thomas equation. Okay, so this is the equation. That is all the data are given to you. And you will be able to plot the breakthrough curve, and you know that what is the amount of water that will incur, that will this breakthrough curve incur in your, and you need to stop your operation. Okay, so after you draw this graph, you can see when is the breakthrough starting and what is the time for you to really stop your operation here. Okay, and this is the Thomas equation plot. So you just refer to this equation here, It is a linear equation, and you will be able to draw or to plot the Thomas equation. What you will get here is this from figure this Thomas equation. You will get the slope and the value. Then finally you will get this value 234.6 per liter. From the figure also, from the Thomas equation figure also, you get the intercept. The intercept is 15.33 per liter. So mass. So this is what is the Q naught, which is 2.932 equivalent per kilogram resin. Meaning how much you remove per kilogram of resin. Mass of resin needed for the full-scale column can be found from the Thomas equation also. So you get this, this is the lab scale. Then you can find the full-scale column by specifying the mass of resin using still the Thomas equation. First, you use this Thomas equation for lab scale system. Then you get all this value. Then finally, you need to use the equation again to determine the mass of resin needed for the full-scale column. Okay. And then these are the calculation. I hope that you go through the calculation by yourself. And another exercise that I want you to do is I want you to copy this. Exercise using your handwritten. Submission, and then the data I want you to draw using whether computer or any graph paper. I want you to draw this. So you need to, this is assignment. Your assignment is easy, that you need to redo this exercise with your own handwriting, and you also draw the graph. Because I just want to make sure that you are able to student. Can you still hear me? Can you still hear me? Student, can you still hear me?
Yes, doctor.
Okay, good. Okay, so this is the exercise that I want you to do. And okay, actually I finished this topic, this ion exchange, actually for this week, actually for the hardness using ion exchange. So I finished. Any question from you? Any question? So I want you to do this homework by writing, by doing the by using your handwritten submission to submit this this exercise. And for tomorrow we have class at 9, right? 9, but I'm so sorry again that tomorrow 9:30 I will have my presentation but it's online at the Ministry of KPKT. So I cannot online with you. So today I want you to study whatever the materials that I will provide in your UKM folio, and I want you to do the exercise of this handwritten solving the problem handwritten, just copy, but with understanding. And then for tomorrow, I need to replace with giving you quiz. Quiz meaning that you have to pay attention for all the quizzes that I give you, because it indicates the type of question, the type of understanding that I want you to have for the material. So it will also indicate what type of question will be asked in your final exam. Because in the design you will have your design of your treatment plant. You will be able to do it, and you also need like some tips what will be asked in your final exam. So by doing the quiz, by understanding the quiz, the assignment, I hope that you can understand the material that you need to make sure that you need to make sure that you understand all the materials that I give. So any question from you for this part? Hardness, water softening, chemical precipitation, and ion exchange. Do you have any question, students? Okay, for the quiz, can I give you Wednesday night, like what we had yesterday, last week? Can I give you a quiz for this part, for this, actually for this techniques for water softening, chemical precipitation, one question, and also one question on this ion exchange. Can I give you on Monday night, like what we had last week, or you want other time? Student, are you still here? Oh, okay. Okay. So I will give you quiz from 9 to 10 about this material. So I want you to really look at the slides that I will provide in the UKM folio for treatment of water hardness. Okay, I think our class, I think I finished with the material, unless you have something to ask. Anything from you? Okay.
Not yet, doctor.
Okay. So very good. So you just do the assignment, submit to me. I will create the assignment part. Assignment part is the same what the exercise that I give you in the slide, but I want to repeat and with understanding, and then I give you the quiz Wednesday night. Okay. Wednesday night. Okay. See you again next week.
Thank you, doctor.
Thank you. Take care.